Alright, so this is the final chapter, chapter 13, nuclear reactions. So let's get into it. First of all, a nuclear reaction is profoundly different than the chemical reactions that we just talked about. During a nuclear reaction, you can actually change the atom. The atom becomes something else. That's one of the things that we're going to see. Now that never happened with chemistry. Okay, this is only nuclear reactions that do this kind of thing. So what is radioactivity? Let's talk about that briefly. It is when atoms will emit particles or energy from what we would call a radioactive or an unstable nucleus. This was discovered by a guy named Becquerel. He was a contemporary of Madame Curie, who helped him after his great discovery, who actually helped him understand radioactivity. So there are three types. This is one of the things that they discovered right away. Is if you have a type of radioactive substance, one of these unstable nuclei, if you surrounded it by lead, the lead mostly absorbs the radioactivity in these directions, in directions not collimated upward, for example, like in this picture. So what you do is you pass the radioactive particles. They didn't really know what they were at first, through a magnetic field, and they found something very profound. One of the particles, and they called it an alpha particle, bent in one direction, and another particle bent in the opposite direction, and it bent much more. It curved a lot faster and a lot more of a curvature, and they called that a beta particle. And then there was one that didn't curve at all, but there was a detector, somewhere over here where it would detect. And now we actually know, of course, what these things are. The alpha particle is a helium nucleus. It's basically the helium atom stripped of its two electrons. And that's coming from the nucleus itself. Okay, that's not some helium that happened to be around or something like that. The beta particle is actually an electron, a high energy electron, but it's an electron not surrounding the nucleus of this radioactive material. That's not what it is. It's actually a beta. It's an electron that has come from the nucleus of the atom. And see, that's where the change takes place. When an electron comes from the nucleus, something has happened, something profound has happened. And then these gamma decays are just high energy photons, the highest energy. If you remember chapter 7, gamma rays are the highest energy of them all in the electromagnetic spectrum. All right, so that was the original discovery of radioactivity. So we have what's called the atomic number, and we've discussed this before, which is the number of protons in an atom. That's the subscript here. Sometimes that subscript is left blank because whatever the substance is, whatever the chemical symbol is, it really defines what the atomic number is. For example, if this was carbon, there would be a 6 down here. There's nothing else that has 6 protons, only carbon. And that's true for everything on the periodic table. However, the mass number can change vastly, these are what we would call isotopes. It's the same atomic number, the same number of protons, but differing numbers of neutrons. So you can have a lot of different neutrons in the atom. Well, not a lot of different ones, but for example, hydrogen 1 has no this number right here, that the superscript is the number 1, and that's the number of the mass number you can think of as the number of protons plus neutrons. And so since there's just one, and that one must be the proton. There's another isotope called hydrogen-2, and that has one proton, of course, but it also has a neutron. This is a fairly rare isotope that we find. Most of the universe, in fact, is made up of hydrogen-1, but sometimes we find some hydrogen-2 and even some hydrogen-3. And by the way, these two isotopes of hydrogen, these are naturally occurring isotopes, actually have their own names. So hydrogen-2 is also known as deuterium. Hydrogen-3 is also known as tritium. Hydrogen-3, however, or tritium, is actually radioactive. So this one's not. Deuterium is not radioactive, and basically it sits around for forever. Yeah. So what else? All right. So let's do an example so that you see how the mass number and the atomic number can give us the number of neutrons. So I thought we would just to change things up a little bit. Let's use potassium, which of course is element 19. So that tells us the number of protons in potassium. Again, you'll sometimes just see the K by itself. You won't see this subscript 19. Let's say we had potassium 39, and that is nice and stable potassium, and we wanted to know the number of neutrons. Okay, so the number of neutrons is going to equal the mass number, which is 39 in this particular case, minus 19. Right, so that's how you figure out the number of neutrons. Okay, so whatever isotope it is, this happens to be a stable isotope of potassium. So that's a pretty simple number. We can easily calculate it. So that is 20. So potassium 39 has 20 neutrons. This is the number of neutrons. The number of neutrons is going to be equal to 20. And so you always do this calculation the same way. Let's do the same element. Okay, so but now I'll go to a radioactive form of potassium. This is potassium 40, and so we want to know the number of neutrons. So it's the same element. It's a little heavier because obviously the mass number has increased by 1. So the number of neutrons is going to equal 40 minus 19. And so we get 21 neutrons. Okay, so 21 neutrons in that particular form of potassium. Let's do another one. I'll just pick another element. Let's say uranium 238. So let's say it was given to us like this. You would look on the periodic table and you say, okay, if I want to know the number of neutrons in uranium 238, it's going to be 238 minus what the atomic number of uranium is. And if you didn't know that off the top of your head, which you're not expected to, that is 92. Okay, 92. So you just look that up on the periodic table, right, for uranium. And let's quickly do this calculation. So when we do the calculation, we get 146. Oops, let's make sure that. So the number of neutrons in this is, by the way, the most common form of uranium, and it is radioactive. All uranium is radioactive. There's 146 neutrons in that type of uranium. All right, and let's say there's another type of uranium. This is actually the deadly kind, uranium 235. Then let's figure out the number of neutrons in that type of uranium. Is just going to be 235 minus 92. Okay, so that's fairly easy to calculate. So that's going to be 143. That's supposed to be a 4. That's supposed to be a 3. Sorry. All right, so 143 neutrons in uranium 235. So there's just some examples of how to calculate the number of neutrons. You need to know the number of neutrons, and we'll see that in just a minute, to calculate or not, to predict whether a particular isotope of an atom is radioactive or stable. Or unstable is the same thing as radioactive. So some of your homework questions ask you to do that, and we'll get into that in just a moment. All right, so let's take a look at, all right, so we just did this. This is what would be called a nuclear equation. Okay, so this is, for example, this is an alpha decay. You can tell it's an alpha decay because the uranium-238 is creating another type of, it's becoming, not creating, sorry, it's becoming another type of atom, which in this case is thorium-90 plus an alpha particle. So you know that the uranium-235 has emitted an alpha particle. All right, so and then there's so there's that one, and then there's a beta decay. Oops, which I thought they were going to show us, and I'll do that in just a second. So you might wonder, what is the neutron doing in the nucleus of the atom? And so and other people wondered this, of course, around the turn of the 20th century. So the early 1900s, people were wondering, what is it that keeps the nucleus together? I mean, you have, two protons that are positively charged, for example, in the element helium, and they don't want to be next to each other because they're both positively charged and they're really close to each other, so the force of repulsion is really, really strong. And then you get to atoms like, uranium, which has, 92 protons, and they really don't want to be next to each other. And so there must be, people figured this out, including Einstein, that there must be another force at play, a force that exists only in the nucleus. And this is the binding force, that it binds protons and neutrons together. It basically overcomes the natural electric repulsion between protons. The neutrons don't have electric repulsion, but what the neutrons do have is this strong nuclear force. Electrons, for example, don't carry the strong nuclear force. So protons themselves, when they're close together, really, really close, so this is like the size of the atomic nucleus, they experience this strong nuclear force, but so do neutrons. So what the neutrons are doing is they're trying to, or they try to stabilize the atom, and in some cases it does stabilize the atom. In other cases it doesn't. If there's too many neutrons or too few neutrons, we're going to find that you're going to have radioactive atoms. All right, but before we get into this this nuclear shell model and predicting stability or radioactivity, let's do some of the nuclear reactions. So for an alpha decay, let's say this is radium-222. Notice that's the way we name it. Of course, this chemical symbol and this atomic number mean the same thing. But now when you're doing these decays, it's actually helpful to write in the atomic number. All right. So anyhow, notice what's happening. Okay. So we have an alpha particle, and basically what you do is it's really, really simple. The subscripts here, the 2, which is always going to be here for an alpha decay, the 2 plus whatever this number is has to give you the atomic number of the radium. Okay, and that's literally how it works. All right. So and also the 4, which is the mass number of helium, that plus whatever this number is must give you what you started with. So the numbers across the